Now, let's discuss dielectrics. Dielectrics, you might ask? What a strange term! Well, it won't be strange for long. Very important in capacitors, practical capacitors, both from a mechanical standpoint and an electrical standpoint. They provide mechanical separation between the plates. That's pretty good, because you don't want those plates touching, or the charge will automatically be gone, and you want that separation uniform also. It gives you a higher plate potential difference before breakdown of the dielectric, or breakdown of the medium between the plates, a little lightning bolt, actually a spark, that destroys the capacitor. So if you exceed the voltage, that would result in an electric field that ionizes the medium. You got a problem. And so this increases that threshold. And it increases the actual value of the capacitance. So that's good, because you want the package to be as small as possible. And if you can have the same capacitance while you decrease, in other words, you can with the same geometry of plates, you put a dielectric in there and the capacitance actually goes up. So you can make everything smaller for the capacitance that you need. Does that make sense? Good. Now, what is a dielectric? Well, I'm going to explain it by giving you some equations here. C is equal to Q over V in general. C0, or C naught in particular I should say, is Q over V naught in a vacuum. Kind of like epsilon naught, epsilon 0. Now, if you take the ratios, so just to clarify, the general is the situation where we put a dielectric in the capacitor. This is when there's just a vacuum between the plates. Okay, the ratio of those two capacities is Q over Q over V0, which is V0 over V. And so you see this ratio is the inverse of this ratio, essentially, functionally. That is the dielectric constant, cap K, as we'll typically just denote it. Now, two charged parallel plates, sigma, negative sigma, and epsilon 0. There's no dielectric in there right now, so we have an electric field. Now, sigma, negative sigma, we're doing nothing with the charge, and that's right, we put in a dielectric. Now what happens? I'm just going to tell you what happens, then I'll explain it. D field goes down. You say, what? What about the surface charge density? Did it decrease? Nope, stayed the same. But yet the E field goes down. So let's write it in there. There is the new E field. Less lines, right? Okay, well, given that is true, V across those two plates, integral of E dot dl, obviously that went down. So K, the dielectric constant, is V0 over V. V0 is what it was over here based on this electric field. The new V is based on this electric field. They're proportional, so it's E0 over E. So that's the dielectric constant of what you put in there. Basically, by what factor did it reduce the electric field? And that factor is the dielectric constant. Now I know you want to know why that happens, so I won't keep you waiting any longer. So let's take a closer look at this dielectric situation. Here's our plates of charge, sigma, negative sigma. And here's our initial E field. I just love that sound effect so much I couldn't resist doing it again. When that dielectric is inserted between the plates, the E field exists in that material, the dielectric itself, and then induces a charge in the dielectric because of the E field. How does it do that? It polarizes the molecules that make up the dielectric. So this E field is pushing on the polar molecules to push the positive over on this side and the negative over on this side a little bit for each molecule. which causes the net effect of having an electric field in the opposite direction. The net surface charge density is thus reduced. So, there is an effective separation of charge due to the induced polarization in this dielectric. The original surface charge density, electric field, polarizing the molecules and making an electric field in the opposite direction as a result of an induced sigma. So we have this induced sigma over here and here. Thus we have that electric field induced. So I indicated that by a smaller, less dense electric field. But electric field, of course, is a vector, so those vectors add. And the result is our new electric field, which is smaller than the original. So by putting the dielectric in, the electric field went down. Now, the net surface charge density is the combination of the original plus the induced. So it's just subtract them, sigma minus sigma I. We also know that the electric field from two parallel plates, E0 is sigma over epsilon 0, surface charge density over epsilon 0. The net electric field is the net surface charge density over epsilon 0. And the net electric field is what I'm talking about over here by just E in the dielectric. Now, E net, epsilon 0 over K. So if you divide the original electric field by K, you get the new electric field. That's how that works. Now, electric field E0 is sigma over epsilon 0 times 1 over K. And that is the net electric field, sigma minus sigma I, over epsilon 0, but that really comes from this. E net is sigma net over epsilon 0. So we have all this, these two terms here, epsilon 0 goes away. And so we can say sigma over K is sigma minus sigma induced as an intermediate result. Solving for sigma induced, we get sigma times 1 minus 1 over K. Now, even though that looks like an awesome equation, you don't need to memorize it. I'm just showing it here for illustrative purposes. And if K, the dielectric constant, is large, then this becomes small, and sigma I becomes very close to sigma. So sigma I approaches sigma, and if that happens, then this induced charge density is comparable to the original, and they tend to negate each other, which means that the potential difference across the two plates goes to 0 because the electric field is going to 0. Catching all that? So now we'll comment on this epsilon 0 that we've been discussing all the time. Generalizing that to permittivity. So I've always talked about epsilon 0 being the permittivity of free space, or the ability of an electric field to exist in that medium. Well, now we have a new medium, and we're going to discuss the permittivity of the medium. We can relate the dielectric constant and the permittivity as follows. Kind of stands to reason. The general permittivity is the dielectric constant times the permittivity of free space, or the permittivity of a vacuum. So let me just relate it to what we have here. So the new permittivity has gone up by the factor K. It's kind of like the electric field can more easily exist in that medium. And now this sounds a little counterintuitive, but therefore there's less of it. It's kind of like less of that electric field to do the same thing. Doesn't have to try as hard. The voltage developed across here is less. And voltage is what tends to cause, current to flow and sparks to fly, that type of thing. So it's a real easy ability for the electric field to exist in here. It doesn't take much of it to do the job, loosely speaking, in all this. The capacitance then is KC0, and That's K epsilon 0 A over D, the geometric definition of capacitance. And so K epsilon 0 is just epsilon. So we have the capacitor with the dielectric is epsilon A over D. There it is. Those are the relationships. And energy density is what it was before, except that now we have 1/2 epsilon E squared. And since E is reduced by this factor epsilon, this whole energy density, because E is squared, actually goes down because of the E squared. So there's less energy density in this situation. Okay, hopefully that gave you some insight into dielectrics. Let's do an example where we mess with some of the features of a capacitor. Here we have an air capacitor, 2 parallel plates, 1,000 picofarad, that's 10 to the negative 12. Here's a pico. Charge on each plate, 4.36 microcoulombs. Remember, you don't add the charge on each plate. If you put charge on one plate, it automatically removes it from the other. They're equal and opposite. You only count it once. What's the potential difference? Well, V is equal to Q over C. That's really simple. 4.36 microcoulombs, 0.001 microfarads. And that gives us 4360 volts. So that's the potential difference. Now let's have some fun and let's keep the charge constant, but grab these plates, or grab one and pull it away so it's got twice the spacing. We're gonna double the separation, but we're not going to let the charge that's on these plates, the 4.36 microcoulombs, we're not going to let it leave and no more is going to come on. The charge stays the same. What's the new potential difference? Well, C, capacity, in the geometric form, epsilon 0 A over D. The epsilon 0 hasn't changed, the area hasn't changed, so C is proportional to 1 over D. All right, so it looks like C just got cut in half, didn't it? Moreover, the voltage is Q over C. Q hasn't changed, but C has been cut in half. So it's proportional. That's enough said probably, but let me just carry this through. It's proportional to 1 over C, which is therefore proportional to D. 1 over C proportional to D. So V is proportional to D. It's a good thing to keep note of anyway. Voltage proportional to distance, but that's consistent with what we've learned. V is integral of E dot dl, right? So for a given E field produced by charge separation, the voltage is proportional to the distance across that E field. So the V is doubled. It's now 8720 volts. So just by separating the plates apart, we double the voltage. That's kind of interesting. The E field has stayed the same, right? Because the charge hasn't changed. The spacing is doubled. Charge has stayed the same, which produces the E field, so the voltage doubles. So you could have done it in relation to that as well. Now this doesn't want to happen on its own. How much work is required to double the separation? Well, the initial energy, 1/2 CV squared, 1/2 C, 1,000 picofarads, V squared, is 9.5 millijoules. So 9.5 millijoules is the energy we have to start with. Now, the new potential energy is 1/2 CV squared, which is 1/2 of C. The capacitance got cut in half. The voltage doubled, and we're squaring that. So that's 19 millijoules. It was 9.5, now it's 19. It doubled. So the change in potential energy, 9.5 millijoules. So that's the work that was required in separating those plates. Let's summarize these results, and I'll use a slightly different idea of actually adding the dielectric as well. So here we have a capacitor, C0, K is equal to 1, it has charge Q0. Here we have a capacitor, it's C. Why? Because we're going to add a dielectric. There it is. And this particular dielectric has a constant equal to 3. The charge is equal to the original charge. In other words, when we put this in, we're not adding or taking away charge from the capacitor. So now we have C0, the original capacitor, V0 across, and the E0, in other words, the electric field. nominal values. When we put this dielectric in, we have 3Z0. The capacity tripled. The voltage got cut in thirds because the electric field was cut in thirds. Now what about the energy? The original energy, 1/2 C0 V0 squared. The new potential energy, 1/2 CV squared. And we have our new values for C. It's 3C0. We have our new value for V. It's V0 over 3, and we're squaring it. That 1/3 negates this, then we do it again, and we get U0 over 3. So the energy of the new configuration went down. So we lost 2/3 of the energy. Oh my gosh, what happened? No charge flowed anywhere. We don't really have any current passing through a circuit here. What happened? So glad you asked. Let's take a look. So let's bring in the dielectric, but stop. Okay, as the dielectric is going in, we have this fringe electric field that's produced by the edge of the plates. That fringe field extends down here a ways. It's going to produce a sigma induced, and that goes down below here. Okay, because of that, there's an electric force that the plates apply to the dielectric. The electric force, as this dielectric moves upward, is obviously going to do positive work because it's moving in the direction it's being pulled. So the potential energy, because of the positive work that the conservative force does, the potential energy goes down, which indeed it did. We lost 2/3 of it, and now the mystery is solved.